Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to waves and oscillations. So in the previous videos we discussed about the basic concepts related to simple harmonic motion. First the important parameters, then the dynamics, what causes simple harmonic motion and what causes a body or a particle to undergo that oscillatory to and fro movement about the mean position. So in this video we are going to discuss about the energy in simple harmonic motion. So we have already discussed simple harmonic motion as the oscillatory to and fro movement of a particle or an object about two extreme points about the center or equilibrium or mean position. Now when it comes to the energy of a signal undergoing simple harmonic motion, in the previous video in the basic dynamics of simple harmonic motion we discussed that when a body is undergoing simple harmonic motion from one point to the other, it is acted upon by a restoring force. Okay, it is acted upon by a restoring force which tries to bring it towards the equilibrium position, and that restoring force is always in the opposite direction to the displacement, the direction in which the object or the material or that particle is undergoing displacement, the instantaneous displacement. And because of this restoring force, okay, the restoring force which this restoring force, it gives rise to one component of the energy in simple harmonic motion which is called as potential energy. Okay, potential energy of the body undergoing simple harmonic motion. Now as the body is in movement, okay, it has certain velocity, and because of that velocity there is another component, okay, because of the motion of the body, in SHM, simple harmonic motion, because of its velocity it has the second component which is kinetic energy. And these two energies are considered when we are considering the simple harmonic motion. And this potential energy and kinetic energy, it gets continuously interchanged from one to the other, while the total energy content of the signal, it is fixed. Okay, as the body or the object it undergoes simple harmonic motion, potential energy and kinetic energy, it continuously gets interchanged, okay, but the net energy, it is always constant. The law of conservation of energy. Okay, energy can be transferred from one form to another, but the net energy can neither be created or destroyed. So the same principle here. Now we know, we have already derived that the acceleration of an object or a body undergoing simple harmonic motion, it is given as this: instantaneous displacement and the angular, we can say angular frequency, considering the motion or the SHM motion. Now, because of this acceleration, the restoring force which acts on the body trying to bring it towards the mean position, it is given by mass multiplied with this SHM acceleration, which is given by minus m omega square y SHM. This is the restoring force, and it is also given by minus k y SHM, where this is the constant, this minus m omega square. Okay, so now under the influence of this restoring force, okay, under the influence of this restoring force, suppose the particle, okay, under the influence of the restoring force in the opposite direction, let's say a particle, it undergoes, let's say, displacement this much by a margin of dy, okay, this, the restoring force acting in the opposite direction, it undergoes displacement dy, small displacement dy. The small amount of work dw which has to be done against the restoring force to do displace that object by a small margin dy, it is given by minus f dy. Now here note that f is opposite to frf, okay, f is in the direction of dy, f will be in this direction, restoring force is in the opposite direction. So this f is opposite to frf's but equal in magnitude, so it is given by minus ky dy, because restoring force is minus ky SHM. We are simply writing it as ky, okay. So it is the same thing, ky SHM and this ky, they are the same thing. Instead of y SHM, I am simply writing y. So this is given by dw is equal to ky dy, and the total work done is integration of dw, and this is for the total displacement, which is given by 1/2 ky square, integration of ky dy, this 1/2 ky square. So this is the potential energy, this is the potential energy, okay. So the potential energy or EP of a particle undergoing SHM is given by 1/2 ky square, or if we just refine it a bit, this instantaneous displacement in simple harmonic motion. So don't get confused with y and y SHM, okay, they are the same thing, instantaneous displacement in simple harmonic motion. Now if we include the constant k in it, in its original form in terms of the mass and angular frequency, it will become 1/2 m omega square y SHM square, this is the potential energy. Next is the discussion related to kinetic energy. Now suppose the velocity of the particle in SHM we have already derived in the important parameters, and we got the value as omega a square minus y square, or y SHM square, let's call it, okay. Y and y SHM, they are the same thing, but here just for your understanding I am writing it in this way, where omega is the angular frequency, y SHM is the instantaneous displacement, a is the amplitude, the maximum displacement from the mean position. So please watch that video related to important parameters where we have derived the expressions for displacement, the general equation, then time period, frequency, velocity, acceleration, everything. So we know that the kinetic energy of any object with certain velocity is given by half mv square. So here it will be half v SHM square. So it will be 1 half m omega square a square minus y SHM square. This is the kinetic energy. This is the expression of kinetic energy. 1 half square a square minus y simple harmonic motion square. This. So we have got the expression for kinetic energy and we have got the expression for potential energy. Okay. So now the total energy. Okay. Total energy is kinetic energy plus potential energy. Okay. So that is for the potential energy first 1 half m omega square y square, okay, or y SHM square, let us call it. Again, don't confuse with y and y SHM, they are the same thing. It's 1 half m omega square a square minus y SHM square. This is the kinetic energy. So here you can see there will be 1 half m omega square y SHM square and this is here minus 1 half m omega square y SHM square. So they will get cancelled and we will have 1 half m omega square a square. This is the total energy of the signal. Okay, this. So as you can see, at any instant in the simple harmonic motion, the total energy, the net energy is always fixed and it always gets interchanged between kinetic energy and potential energy. Okay. So here for a particular object, okay, a particle in SHM, mass is fixed, okay, maximum amplitude is fixed and the angular frequency is fixed. So the total energy, the net energy for the entire duration of SHM will be fixed, but it will get interchanged from one form to the other. Now here if we want to represent the energy of a particle in SHM in graphical form, it will be like this. So here if you notice the blue plot, both the kinetic energy and potential energy, their graph versus displacement, the energy, kinetic energy and potential energy versus displacement, it will always be in the form of a parabola centered around y is equal to 0. Okay, so this is displacement. Okay. This is displacement and this is energy. So here it is a parabola centered around y is equal to 0. This blue one is for kinetic energy, red one is for potential energy, and the straight line parallel to the displacement axis, this is for the total energy. Okay. So here the kinetic energy, as we have already derived the kinetic energy expression, the kinetic energy will always be like this: 1 half m omega square a square minus y SHM square, and potential energy that is equal to 1 half m omega square y instantaneous displacement y SHM whole square. Okay. So this is the graphical representation of the energy content of the signal in simple harmonic motion. Now here at YSHM is equal to 0 at the center position or the equilibrium position. Kinetic energy will be just we substitute YSHM with 0 and will become 1/2 m omega square a square. Okay, and when this will become 0 at the equilibrium mean position, potential energy will be 0, as see here, it will be 0 and will be maximum at the equilibrium position. Kinetic energy will be maximum at the equilibrium position, potential energy will be minimum 0 at the equilibrium position. At the extreme positions, y is equal to plus minus a. If we substitute here a, kinetic energy, YSHM with a, it will become 0, kinetic energy is 0 at the extreme points, and here at the extreme points potential energy is maximum, equal to the total energy, the maximum energy, the total energy here, which we derived. Okay, so this is the whole thing for the entire duration of the simple harmonic motion, the to and fro movement. Both kinetic energy and potential energy continuously gets exchanged, but their sum, the total, is always fixed. Okay, this. And this is the whole thing related to the energy content of a signal in simple harmonic motion. It has two main parts: kinetic energy, potential energy, and the sum. Both kinetic energy and potential energy, they get continuously interchanged. Potential energy because of the restoring force, work done against the restoring force, kinetic energy because of the velocity, and total energy is the sum, which is dependent on the mass, angular frequency, and maximum amplitude, which is fixed. That's why total energy is fixed. So this is all about the energy of a body or an object in simple harmonic motion. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.